Hello guys, hope you are doing well, and as always, if you are new to my channel, I would humbly request you to subscribe to my channel and click the bell icon so that you shall be able to see all the latest engineering videos that I will upload on my channel. Thank you. Okay, so the problem that we have on our hand today is basically analysis with a spring and VDL on an SIP. Okay, so here if you look at it, we have got this beam, and this beam is loaded with a VDL, variable distributed loading, and there is a spring which is supporting this beam. And on the left hand side, if you look at it, there is a fixed support. The loading maximum value is omega, which is in newtons per meter, but along the spring there is also a clearance which is termed as y naught, and then the spring starts. Okay, so this is the problem, and if you look at it, there are three unknowns of the fixed support and one unknown of this spring reaction is there. So 3 plus 1 makes 4 unknowns. So this, because it has 4 unknowns, so this beam, when it will be solved, it will be solved under the heading of statically indeterminate beams. Okay, so let's start the problem. Okay, the steel beam has modulus of elasticity 200 gigapascals, is fixed at the left end. This is the left end where it is being fixed. Uh, and is loaded and supported. It is loaded, is supported by a helical spring, and if you look at it, this is the helical spring where it is being supported. Okay, so now we need to determine the reactions of the spring B on the beam if the following numerical data applies. The second moment of area that is being given to us, if you look at it, is 20 into 10 to the power 6 millimeter 4. The length is 5 meters. This length is 5 meters. The loading value omega is 3 kilonewton per meter, and the clearance deflection is y naught is 5 millimeters when the beam is unloaded. Okay, because when it will be loaded, this clearance value will be closed. The gap will be closed. The spring modulus, this spring K value is given as 1200 kilonewton per meter. So before starting, we should be able to see the deflection equation of this system. Okay, because they are asking for us that we need to determine the reaction of the spring B. So for reaction, basically we have to calculate the deflection of the spring in order to get the reaction. So if you look at the equation of this system, can be called as the whole beam. When it will undergo deflection, it will be equals to the deflection because of this clearance plus the deflection because of this spring. Okay, so if we add up these two deflections, we will be able to get the total deflection of the beam, and this equation will be very much important when we are able to calculate the reactions of this statically indeterminate beam. Okay, so once we have understood this, now we can see, if you look at it over here, uh, that this is our beam. Okay, this is our beam and this is the loading omega. It will have a resultant value because it is a triangular loading omega L by 2, and it will be acting at L by 3 from the point A. These three reactions AX, AY, MA are the reactions of the fixed support, and the R is the reaction of the spring. Okay, and see, very important point, the y axis is on the this is the direction of the y axis. If we move downwards, the y axis will be negative. This point will be utilized a lot. Okay, if we, since we need to calculate r, what we can do is we can make a cut at somewhere point this. If we can make a cut over here, so the now the length of the spring will be x, and because of the cut there will be a shear force, and one shear force and bending moment, uh, resisting bending moment being generated, and this is the shear force VO and MO, which is acting at point O. Okay, but since we have made a cut over here, the resultant value of this loading, the maximum value of this loading will not be omega, it will now be omega naught. Okay, and this is the length x and this is omega naught. In order to proceed further, and just to let you know, because it's a triangle loading, it will be acting at this point, and which will be x by 3 from the point O, and its value will be half base into height. So half the base is x and the height is omega naught. So if you look at these two triangles, we can say that they are similar triangles. So we can make a ratio out of it, is that omega naught over x will be equals to omega over L. Okay, this is L by 3 and 2L by 3 added makes L. So here it is. If you look at it, you can easily say that omega naught will be equals to omega x upon L. So now what you will do is basically we shall be interested in calculating the moment summation at O in order to calculate this value R. This is our target that we needs to calculate. So, okay, so basically we now proceed. Summation of all those moments at O will give you from here. If you look at it, it will be basically uh, minus m. This is direction. This is going to be minus m plus this m naught is basically equals to m. Okay, if you look at it, you can say that m is equals to m naught. So minus m plus r into x plus r into x minus basically this is the force half omega naught x half omega naught x, and this force momentum will be x by 3. This is x by 3. So now what we can say is that minus m plus rx minus this force half omega, and this omega naught can be given as value as omega x upon L. We can put it over here into x into the momentum x by 3. So now this m, remember this m is basically the same as m naught. Okay, so this m, which is actually the resisting moment, is equals to rx minus, simplify these two terms in the bracket, 1 by 6 omega x cube over L. This makes our equation 2. Okay, now we need to calculate differentiate this equation 2 with respect to the force R. Okay, when we differentiate it, we will get tau, because we are differentiating this function with respect to the force R. This will be treated as a constant, and dawa m over dawa R, when applied to this these two terms, it will be equals to simply x. Okay, so dawa m by dawa R equals to x. This is equation 3. Now the deflection equation of the beam could be given as deflection of the beam is equals to 1 over EI 0 to L m dawa m over dawa R into 2x. Okay, this is basically nothing but it is the Castigliano's second theorem, which is applied to the beams for deflection calculation. Okay, so now we simplify it. 1 upon EI 0 to L, we put the value of m. This is the value of m that has been calculated. This is the value of m, we put it here. Okay, and we multiply it with basically the momentum, the differentiable dawa m over dawa R value, which is x into dx. Okay, now we multiply x with this terms in the bracket, we get 1 over EI 0 to L rx square minus omega x4 over 6L. Okay, so now we again proceed, simplify it further. 1 upon EI rx cube over 3 minus omega x5 over 30L, and apply the limits 0 to L. So we get the final answer as 1 over EI RL cube over 3 minus 1 over 30 omega L5 upon L. Okay, now what we can do is basically we know that this whole term is basically equals to the beam deflection when we calculated it, because you see this is basically we have already written, this is the term delta B equals to this. So now this is equals to the beam deflection, and now we need to calculate these terms, deflection because of clearance and deflection because of spring. And once we calculate this, we can put the value of this beam deflection over here, the deflection of clearance value over here, and the deflection of spring value over here in this system deflection equation. So deflection because of the spring can be calculated as F equals to K delta. Here it is R equals to K delta. So deflection comes out to equals to R upon K. But remember, we are putting a minus sign here because the negative sign, because the spring, when the beam will bend, it will basically compress the spring. So we put a negative sign. Clearance's value is 0.005 of a meter. Okay. So the reason being negative because this is the positive y, and the clearance which is acting, if you look at it, this is the clearance which is acting in the negative, is lying on the negative y axis. Positive y is here and negative y is bottom, is below the positive y axis. So we put it a negative sign. So now input data in the system deflection equation. Now we have calculated clearances, we have calculated deflection because of spring, and we have calculated the deflection of the beam. So this equation, the clearance value and the spring value all will be put into this equation. So when we put it, we get that beam deflection equals to R into, now we put all the numerical values which are being provided to us over here, I, L, omega, Y naught, all these values, and E in the uh, main system deflection equation. So when we put it, we get R into 5 cube over 3 into 200 gigapascal into I. This I has been transformed to meter, 20 into 10, meter 4, 20 into 10 to the minus 6 minus uh, what we have got, omega L4, so 3 into 10 to the power 3 into 5 to the power 4 divided by 30 E 210 to the 9 into 20 into 10 to the minus 6. Now the entire steppings has been shown to you. Simplified this equation, then we simplified this beam deflection equation over here. The simplified value is this, and then we can basically being able to get the reaction, which was R equals to 945.7 Newton. Okay, so what does it further explains to us? It explains to us that when this load, which is basically omega 3 kilonewton per meter, will be applied on this beam, the reaction that this spring will provide to it will be 945 newtons. I hope you have understood this typical statically indeterminate beam with a VDL applied on it, and your concept will be further enhanced. I thank you all, and I hope you all have a wonderful day. Allah Hafiz.